All right, everyone. This is the video lecture to go along with the chapter 20 and 21 notes. I'm combining these two chapters together to go over the important things that we absolutely need to cover. Those topics will mostly be about inductance, electromotive force, which is to say voltage, and also transformers. Electrical transformers, not the ones from Planet Cybertron. This will be the last topics on electricity, which means that we will be having our electricity test in the near future. This week, the week this goes up, the week this is meant for, that will be the week of the 6th through the 10th, will be spent going over this material. Towards the end of the week, we may start transitioning into test prep, just to go ahead and I might go ahead and start posting test prep materials. Next week, the week of the 13th through the 17th, we will begin with test prep. I will make sure that there is a review guide posted with a list of topics that will be on this particular test, give you practice questions that you can work on, and towards the end of the week, I will post the tests. Towards the end of the week at the latest, I will post the test to WebAssign. It will be on WebAssign. Now, you only have to post your answers through WebAssign. And it's not going to auto-grade it because I know WebAssign is just going to get it wrong. I'm going to grade them all myself, but if you submit all your answers through WebAssign, it's convenient for me because all your answers are going to be in one place, and I can just check them off very quickly. Now, obviously, I give a lot of partial credit on my tests. So, after you finish with the WebAssign portion of the test, you'll have a certain amount of time to where it'll kind of work like a long quiz on WebAssign. You'll have a certain amount of time to do it, and once you open it up, the clock starts ticking, and after you are either completely finished or after the timer runs out, you can send me photos of your scratch work, so that if you didn't get a number answer completely right, I can go in, check your scratch work, and assign you partial credit for the question. So I will also be discussing more of this with everybody as we get closer and as details get finalized. So that will be happening. That test will be happening. Will be available for you to take online from during the week of the 13th through the 17th. The week after that, we are going to wrap up the semester and talk about waves and optics. Those are things that will be on the final exam. So, since this is our last electricity chapters, since we're actually covering 2 chapters in this set of notes, let's go ahead and get through it. Your slideshow for this particular week is inductance and EMF. So let's get started. So if you open up your slideshow, slide 1 is the title slide. Slide 2 is a brief synopsis of magnetic flux. Flux is what we ended the chapter 20 notes with. And brief synopsis, magnetic flux is just a measure of how much magnetic field is passing through a given area. And you just calculate it using the formula flux equals magnetic field times area, and in order for this to work, the 2-dimensional surface area that the magnetic field is passing through has to be perpendicular to the direction of the field itself. So if this piece of metal was oriented vertically, the field would have to pass horizontally through it within the x-axis. If this piece of metal was tilted so that it was parallel to the field, there would be no flux. These two things need to be perpendicular to one another. Now, if you move on to slide 3, slide 3 brings up a concept known as Faraday's law of inductance. And I want to draw your attention first to the first quote on that page. Nature abhors a change in flux. When an object has a certain amount of flux flowing through it, it's comfortable that way. It wants the flux levels to stay that way. it starts acting strangely if you start trying to change the flux through some means. So, to demonstrate this, I have, and I need to adjust the camera view, sorry. I have here a ring launcher, and what this machine does is, this is an electromagnet. This is an electromagnet, and that means that it's a device that when you run current through it, it begins producing a magnetic field. So under normal circumstances, none of these materials actually are magnets. And to prove that, I have removed the iron core from the ring launcher. It's not sticking to anything. This is just iron. It's just normal iron. Additionally, these two rings here are made of aluminum. These are aluminum rings. And something to note about regular aluminum is that it is not magnetic. So this is just a disc fridge magnet. It does not stick to these aluminum rings. It will, however, stick to this iron core. The iron core is just part of how the electromagnet works, but this core itself is not a magnet. It's just made of iron. And to prove that, see this push pin here? No magnetic attraction. This iron core itself is not a magnet. But the ring launcher itself has these copper coils on it, and since it's plugged in and powered on, there's electric current running through these copper coils. That's going to produce a magnetic field within this iron core right here. Now, these aluminum rings aren't magnetic. These are not magnetic. I'm going to get the magnet back out, and I'm going to prove there is a magnetic force here right now. So my little disc magnet is sticking to this system, so there is a magnetic field present, but it's not affecting these rings. Now, there's a certain amount of magnetic field being given off by the actual coil here. So right now, because there's a certain magnetic field passing through the area of this ring, there's a certain amount of flux in the ring. Now, there's a switch right here on the front of the ring launcher. When I throw this switch, the machine is going to very rapidly reverse the direction of current. That's going to reverse the direction of the magnetic field. That's going to very quickly change the flux in the ring, because flux depends on the fact that the magnetic field and the area it's passing through are perpendicular. But if you change the direction of the magnetic field, that's going to swap you from a big positive number to a big negative number in terms of the flux. That is a very big change. Now, nature does not like changes in flux. So when I flip the magnetic field, when I swap the direction of the field, and I create a very large change in flux, the ring flies off. Nature does not want the flux to change, and so a force is generated to try to balance everything back out. So there's just a force that throws the ring straight up. So changing the flux in a system creates a force to try to fight against that change in flux. The ring wants to be back where the flux is, where it was. So this force is produced to try to push it back in that original direction. That has the side effect, however, of blasting the ring off of the ring stand. It's a little frustrating when they don't fall in the line of sight of the camera. So I'm going to stand back here and do it one more time. Hope that one was a little more visible. So, when you change the flux passing through something, there's usually some sort of a force as a result of that. That is sort of the system fighting against you changing the flux. And you can change the flux by either changing the amount of magnetic field or by changing the area that the field passes through. If you can change either of these, you can change the amount of flux, and that's going to create some sort of a side effect. That side effect is measured in Faraday's law of inductance. So, keep looking at slide number 3, and I'll keep explaining. So, in addition to flux, in addition to the formula for flux, we also previously discussed that when a charged particle enters a magnetic field and it is moving perpendicularly to the direction of the field itself, there will be a force between the field and that particle. Now, uniquely, the system doesn't actually care if it's the particle that is moving or if it's the magnetic field that is moving. Because the way that relative velocity works, it doesn't really matter which one is moving from the perspective of the other object. It just matters that there is some velocity between these two things and the motion is perpendicular to each other. What that means is, if you look at the picture on slide number 3, the picture that has what is Faraday's law written on it, what that picture demonstrates is, in part A of that image, someone is holding a bar magnet next to a wire loop. Now, if the magnet is being held still and the wire loop is being held still, nothing happens because there's no relative movement. In this particular setup, there's no current in the wire. That wire is not connected to a battery. It's connected to something that is reading the current passing through it. Yes, it is currently reading the current inside of that wire. And as long as the magnet is not moving and there's no voltage applied to the circuit, there is no movement of either the electrons in the circuit or of the magnet. Now things change. We have previously discussed what happens if you expose a magnetic field to a wire that has current running through it. So if I hold a magnet next to a wire that has current running through it, there will be a magnetic force. But I can also, as indicated in this picture, hold a magnet next to a wire with no current running through it. If I just hold the magnet and the wire still, nothing will happen. But if I begin moving the magnet around, if I move the magnet, that starts moving and changing the magnetic field. That means now there is some relative velocity between both the field and the charged particles inside of the wire. It doesn't really matter which one's moving. As long as something is moving, there will be a force to accelerate the particles. So, you can have a stationary wire with no current running through it at all. And if you take a magnet and move it around near that wire, and the magnetic field around the wire is now changing, that will create a current through the wire. Because since the field is changing, since there's now a relative velocity and a magnetic field, there will be a force to accelerate the charges inside of the wire. And once the charges start moving, you have electric current. So Faraday's law of inductance tells us that you can use magnetic fields to create current in a system. More specifically, it creates a voltage in the system, and that voltage then drives a current. Now, On slide number 3, there's a few formulas. The first thing that it lists is a reminder of a sort of commonality of terms. These slides are going to alternate terms, alternating between the terms of voltage, electromotive force, and also this symbol right here. These all mean the same thing. If the slideshow says electromotive force or uses this symbol, that means voltage. And I'm going to call it voltage. Just want to address it now to make sure that everyone's okay with that. These things mean voltage. So, according to Faraday's law of inductance, if you move a magnet, if a magnetic field around a wire is changing, that will create a voltage in that wire system. The voltage created will depend on the number of coils in the wire times the change in magnetic flux passing through the loop divided by the time that this process takes. How long it takes you to change the flux by this amount. And so as you move the magnet around, you're changing the amount of magnetic field passing through the area of the loop. That changes the flux. If you change magnetic field, you change flux. If flux changes, if the flux passing through a loop changes in some amount of time, you will create a voltage within that system. This is called an induced voltage. And this is one of the ways that electrical generators work. Most power plants in the United States, regardless of whether or not it is hydropower, coal burning, oil burning, or even nuclear, all of those power plants, the main goal is to somehow to get a turbine to spin. When you spin that turbine, you are spinning a coil inside of a magnet. The magnetic field changes. There's relative velocity between the coil and the magnetic field. That creates a voltage in the wire, and that therefore drives a current through the wire. And so this is at least partially the principle that allows us to generate all of our electricity. Now, moving on, slide number 4, just re-emphasizing the point from a moment ago. Changing the magnetic field around the loop is what causes this effect. It creates a voltage in the system, and because there is now a voltage, that's going to start driving a current through the system. Moving on to slide number 5. Slide 5 is just a reminder of the right-hand rules, the rules for determining what direction a force is going to be based on the direction the charges are moving and the direction of the field. So that is just review. We now get to slide number 6. There is the picture on slide number 6 is a very simple kind of generator. It's a very simple generator. I'm going to put it on this half of the board right here. So, the circuit pictured has a resistor in it. It has a certain wire that is L length long. That wire is connected to a handle. This is a handle, something that you, a user, are designed to be able to grab and push. And so this is a handle that is on a sliding bar right here. We are able to push this bar either towards the resistor or away from this resistor. And there is a magnetic field enclosed within this device. So, this is basically a wire loop. This is an area, and magnetic field is passing through that area. So we have a certain amount of flux inside of this system. If I was to grab this handle and push, that would shorten the length of these sides. If I move the handle closer to the resistor, these sides are going to get shorter as the handle draws nearer. That's going to change the amount of enclosed area as these sides get shorter. By changing that area, I am changing the flux passing through this device. And if I change the flux in a certain amount of time through this loop, I create a voltage within the system. Now, it takes a certain amount of force for me to be able to push this particular device, to push the handle inwards, because, again, as the previous couple of slides said, nature abhors, which is a very strong word for hates, nature hates a change in flux. So when I push in on this handle, the system is going to push back. Like with the ring launcher, when you change flux, the system exerts a force. If I push on the handle to change the flux in the system is going to push back on me. It's going to exert a force back out. So if I push in with some force, the flux is going to push back out with an equal and opposite force. But if I am able to push the handle in with some velocity, that's going to reduce the area, that will change the flux, that will create a voltage within this circuit. There's not actually a battery here. There's no battery, there's no voltage source. The voltage would come from me pushing the handle. Pushing this handle, as long as it's in this magnetic field, will create a voltage. And that will create a current through this resistor. So this is a very simple type of generator. This is a simple machine where if this was, say, a light bulb, and I pushed in on this handle, I could turn the light bulb on. My mechanical energy pushing into the system would create electrical energy, create an electrical current circulating through this resistor. So this is a very, very simple kind of generator. If you've ever had a sort of hand crank flashlight, it's a very simple principle. You're just turning your mechanical energy, the energy of you pushing, into electrical energy. So, I'm going to briefly summarize the formulas listed on that slide, listed on slide number, that is slide 6, we're on slide 6 right now. So, on this particular slide, we have the voltage created in this generator by me exerting a force. The voltage created in this generator is going to be equal to negative times the magnetic field passing through the circuit times this length, the length of this wire. This is the length of the side that isn't changing. So when I push in on this handle, these sides get shorter, but this side stays the same. So this L with the resistor that doesn't change is what goes into this formula. And last but not least is the velocity V. This is not a big voltage V, this is small velocity V. So to figure out how much voltage I'm going to create in this circuit, I need to know the magnetic field passing through it, the length of this side, and how fast, the constant velocity that I am pushing the handle at. Now the second formula listed is just Ohm's law. So V equals IR, therefore I equals V over R. So the second set of formulas there is just Ohm's law again. The last formula on this page, force equals current times magnetic field times length. This formula, if I push onto the handle with some amount of force, that's going to be equal to the current in the system times the magnetic field passing through this circuit times this length. So this formula tells me how much force I need to push the system in order to create that voltage from earlier. Subsequently, due to Newton's third law, that means this is also the amount of force that the system is going to push back out as well. So if I had to push in with 5 newtons of force, the system is going to push back out with 5 newtons of force, because nature doesn't want the flux to change. It's going to fight me as I try to change it. So, these are all the formulas from this slide. We're going to do a quick sample question to utilize these formulas. I'm going to erase this piece in the middle here so that we can use these formulas. So, slide number 7 summarizes some of the things that I just said. This will create a DC current. That means that this current is direct current. It's just going to travel from the bar through the resistor back to the bar. This is just a closed circuit, and everything, the current is all going to travel in one direction. So this is a very simple DC generator. Now slide number 8 is our sample question for these formulas. So we're going to take this same drawing, we're going to add some numbers to it to start using it. So in this particular circuit, this length right here is going to be 10 centimeters. So the side that doesn't change, this length of the side with the resistor is going to be 10 centimeters. The resistor itself has a resistance of 100 ohms. And the magnetic field passing through this device equals 135 Tesla. So, first question that we're asked is, I want this to produce a voltage of 9 volts. This resistor is a device that I have plugged into the circuit that needs 9 volts to operate. So, if I want 9 volts, what is the velocity that I need to compress the handle with? How fast do I have to move that bar for the voltage that I create for the induced electromotive force to be 9 volts? So, we know L, we know R, we know B, we know what we want for V, for our voltage, and this symbol means voltage. This formula here will let us solve for our velocity. So, electromotive force, we want 9 volts. This symbol means electromotive force, means voltage. So, anywhere you see this, you can plug in your voltage. We want a 9 volt voltage. Our magnetic field is 135 Tesla. Our length is 10 centimeters. Convert that to meters. And then we solve for velocity. Don't worry about the negative sign yet. I will explain what that represents in a second. So, with these numbers, we calculate our velocity, and this is little v velocity. I'm going to try to make my notes clear on that. Little v velocity. This is big V voltage. This is little v velocity. So, 9 divided by 135 divided by 0.1, and that gives me an answer of negative 0.67 meters per second. Now what the negative sign here means, it's referring to direction. So normally we consider this way to be positive, this direction would be negative. So I need to move the in order to create this voltage, I need to compress pull in the bar at this velocity. So the negative sign just means direction. This is the magnitude of velocity that the bar needs to be moving at to produce our required voltage. Very good. Next question. In order for this to happen, in order to create this, in order to create this 9 volts, in order for me to actually push it at this rate, how much force am I going to need to apply into this system? So, what we want to know is force. And only one of our formulas so far has force in it, this one right here. So, we're solving for force. Now we know the length of our constant side. We know the magnetic field passing through the circuit. We need to know how much current is passing through the circuit. Now, thankfully, in order to find current, we know the circuit voltage because we want it to be 9. We know the circuit resistance because we know the size of our resistor. So, we just need to use Ohm's law to find our current. We will then plug our current right in here to find the force required to push that handle to create our 9 volts. So, current is going to equal our desired voltage over the resistance. We want 9 volts. We have resistance of 100. That means that the current in this system is going to be equal to 0.09 amps. And that is the current that we can plug in here. So, force is going to equal that current, 0.09, times our magnetic field of 135 Tesla, times our constant side length of 10 centimeters, which is 0.1 meters. And so our force, the force that we must apply to this system in order to create the desired voltage of 9 volts, is 1.215 newtons. So we have to push with about 1.2 newtons of force in order to make this voltage happen. Now conversely, that means the system is going to try to push back with that same amount of force. This is Newton's third law. We will push in with this much force. The system is going to push back with that much force. That's because the system is trying to resist the change in flux from us reducing the enclosed area. But as long as we can exert this much force, we will cause the bar to move in at this velocity and we will create our desired voltage. Very good, everybody. Well done. All right, so the previous example was a DC generator, and DC is direct current. A direct current system, a system with direct current flowing through it, all the current just continually flows in one direction. Most of the circuits we've been working with so far, all the battery circuits that we've built, the way that your houses are wired, that's all direct current because the current is just traveling from point A to point B. I'm now going to show you on slide 9 the basics of an AC motor. An AC stands for alternating current. And the main feature of alternating current, and we've discussed this briefly, is that instead of the current all traveling in one direction, the current and the voltage are constantly switching directions. So the voltage is constantly going from positive to negative, and that causes the current to move forward sometimes, and then backwards sometimes, and then forwards and backwards continuously. And the reason we do this is because it's actually easier to make alternating current than it is to make direct current. With the previous example, with the DC generator that we just looked at, I can grab this handle and I can push inwards, But eventually, I'm not going to be able to go any farther, and I'm going to have to pull the handle back and reset it. There's a limit to how much DC I can make at one time with this particular generator. But on slide 9, that shows the basics of a very common type of alternating current generator. And for that type, and this is what the next example is going to be about, for that type of alternating current generator, these blocky shapes to the side here are magnets. These are magnets producing a very specific magnetic field. And that magnetic field is being exposed to this wire loop inside of, sitting between the magnets. So there's magnetic field passing through this loop, and when field passes through a loop, you get magnetic torque from last week. So the magnetic torque on this loop is going to cause it to start rotating. Now, just outside of the loop is a coil. This coil has, n number of coils. It has some cross-sectional surface area. And the loop passes through the coils until on the other side of the loop it connects to an output shaft, and the motion... Oh, sorry, this is a generator. My bad. What happens here is, as this starts spinning, as this system is spinning, and there's a certain amount of current running through it, this spinning creates a rotating magnetic field inside of this coil right here, and that creates current inside of the coil. But because this magnetic field is constantly making it spin, it is spinning, the direction of that current is going to constantly keep switching directions. And so this will create an alternating current. This is AC. But the benefit here is, unlike this previous machine where you have to push it in and then pull it back to reset it, you don't have to reset this. It can just keep spinning. So AC is more convenient to make. It's also more convenient to send over long distances. So all of our power companies send electricity out to houses all across the city as alternating current. And then once that AC gets to your house has modules attached to it called transformers, which can turn it into direct current, which is then used in all of your appliances. So we're now going to do a little bit of math related to this type of a generator, just to show you the math that goes into it. So, the formula for the voltage produced by this type of a generator, so voltage equals number of coils in the coil itself times the magnetic field of the magnets times the cross-sectional surface area of the coil times the angular velocity, that is to say, how fast is the coil spinning, how fast is the coil currently spinning, and actually this formula right here is the formula for the maximum voltage that will be produced by this system. This will tell you what the voltage will be at its greatest peak and also what it will be at its lowest. Because if you see on, there's a graph on this slide, on slide 9, that graph shows that the voltage is going to oscillate from 0 up to its positive maximum, down to its negative maximum, and continuously up and down, back and forth, because it is constantly switching directions. The positive maximum and the negative maximum are both the same number. And this formula right here will tell you that number. the maximum voltage number that you can get out of this. But there are spots on that graph where you are between the two peaks where you're not at maximum, because those are the points where the system is mid-spin, things are still changing direction, and we're not in the position that creates the maximum amount of voltage yet. So, this is for the maximum voltage the system can produce. There's a separate formula for voltage at a specific point in time, and we modify the formula by multiplying it by sine of angular velocity times time. This formula just tells us what is the voltage currently at a specific moment. This formula will tell us the maximum, which is most of the time what the power company cares about. But this will tell us what it is at a specific moment. So you see on that graph there, as you're graphing, voltage on the vertical axis and time on the horizontal axis, this graph can tell you what is the voltage at 1 second, what is the voltage at 2 seconds. And that voltage is going to keep oscillating up and down between its two maximums. This formula just tells you what it is at a given moment, at a specific t. Now, slide number 10. To utilize this formula, well, these formulas, plural, very quickly. So let's say we're going to put some numbers on this coil, on this generator that I've already drawn. We want this generator to give us a voltage of 120 volts, because that is the standard voltage of an American U.S. outlet. We want this thing to produce the voltage we need for our standard U.S. appliances. We're going to build this generator out of magnets that give off a magnetic field of magnets that give off a magnetic field of 50 Tesla. And we have a coil here. This coil has 200 turns. It has 200 loops. And it has a cross-sectional surface area of 0.0001 meters squared. So, first question. We've built this generator. No problem building it. But now we need to know how fast we need to spin it. We are going to, this end right here would sort of be the side that is connected to the water wheel. So, or the wind turbine, the windmill. Point is, this is the part right here where something has to make this end move. Something has to make this end move. That's going to then force the loop to start moving within the coil and within the magnetic field. That's going to then create current inside of the coil. So the question then is, how fast do we need to make this thing spin to create our desired output voltage of 120 volts? So we want our AC voltage, our alternating current voltage, to have a maximum of 120. So we want to use this formula right now. We want to know we want the maximum of the system to be 120. We want it to oscillate between positive 120 and negative 120. So this is the formula that we want to use. So, our desired 120 volts is equal to number of coils, that's 200, times magnetic field, which is 50, times our cross-sectional area, which is 0.0001 meters squared, and then times omega. Omega is our angular velocity. It's the same angular velocity from Physics 1500. We can solve for omega, and that will tell us how fast we need to spin that wheel to create the desired voltage. Actual people who work in power plants need to specifically cause these turbines to run at a specific speed so that we create the desired voltage. So, 120 divided by 200, divided by 50, divided by 0.0001. That gives us, interestingly, an angular velocity of 120. Now remember the units for angular velocity, radians per second. Radians per second. So these two numbers being the same is a coincidence. That's just the way I wrote the problem unintentionally. Don't read into that. So this is the desired angular velocity. This is how fast we need to make that wheel move. Now, the second question asks, once we get it up to this speed, what will be the voltage at 0 seconds of operation, then at 1 second, then at 5 seconds? So to solve for those, we want to look at the other formula right here, because this tells us what the current voltage is at a specific moment in time. So let's use that formula. We plug in our number of coils, which is still 200. Our magnetic field is still 50. Our cross-sectional surface area is still 0.0001. We now know our velocity, our desired velocity, angular velocity is 120. Now we multiply that by sine of 120 times time. That should be a t, I'm sorry. So 120 times time. And for each of the 3 times listed, you would simply plug in a different time into that formula. And if you plug in 0 seconds, 0 times 120 is 0, and sine of 0 is 0. So at 0 seconds, we haven't produced any voltage yet. It hasn't actually moved. We only just turned it on, and it hasn't had time to move yet. So at 0 seconds, there's no voltage yet. At 1 second, oh, you should make sure that you are in radians mode for this. You should make sure that you are in radians mode. So at 1 second, you plug 1 in here. So that would be sine of 120 times all of this. That would give you an output voltage of about 70 volts. If you plug in 5, that would give you an output voltage of about 5 volts. So the voltage is going to change based on when you look at the graph. But the maximum, what it's oscillating between, will be 120. We are running it at the speed required to create 120 volts worth of alternating current voltage. Okay. Now, moving on to slide number 11, actually. This is a slightly new principle called induction from Faraday's law of inductance. Now, the second that you turn on your light switch, there's a certain voltage for the whole circuit. The circuit has a certain total resistance. And so according to Ohm's law, V equals IR, there's going to be a certain total amount of current within the circuit. But as soon as you turn on that light switch, the current does not immediately go from 0 to maximum. When you open the floodgate to a river, the door cannot immediately go from fully closed to fully opened immediately. And the water cannot go from 0 to completely moving all of it at flow immediately. There's sort of a waiting period. And a circuit's induction, it's a circuit's inductance, is the measure of a circuit's tendency to need to boot up. Every material has certain inductive properties. like how every material has certain resistive properties. Every material resists current flowing through it, and every current needs just a little bit of time for the current to be able to start flowing through it. Some materials take longer than others. You're not going to have to worry about a constant table, though. Don't worry. Because rather than tracking what material something is made of, there's a different formula that tells us the inductance of a specific object. An object that has a specific known inductance is called an inductor. And a common example of an inductor is actually just a solenoid. Basically, those wire coils that we talked about last chapter, a solenoid is an example of a conductor. And when you have a solenoid, when you have an inductor wired into your circuit, the inductance of that inductor affects how long it takes the current of the circuit to go from 0 up to its maximum. Induction is sort of like the opposite of capacitance. If you have a capacitor plugged into your circuit, the capacitor begins when it is at its minimum charge. The capacitor lets all current through it. But as the capacitor begins filling up, it stops letting current through. So if a capacitor is in your circuit, the current drops over time. If you have an inductor in your circuit, then the current starts out slow, but then it slowly increases to maximum as the inductor warms up. Once the inductor is fully warmed up, it will let the maximum current that the circuit can have through it. Once the inductor is fully charged, it's like it's not there. Unlike a capacitor, where when it's fully charged, it's so there that it's blocking the current. So inductors are sort of the reverse of capacitors. All circuits have some amount of inductance, because like how every material has resistive qualities, every material has inductive qualities. And this is why in every single circuit, the current always takes just a tiny bit of time in order to sort of warm up. If you just put an inductor into your circuit, it's going to take a little bit longer to warm up, but if you know the inductance, you can figure out how long that is. So we're now going to start doing some math for inductance. So on slide 11, we have some formulas for the inductance of an object. The inductance of an object. So, the variable for inductance is L, because we ran out of good letters a while ago. I'm sorry. And the unit for inductance is henries. We measure inductance in units of Henry, and that is abbreviated to a capital H. So this is another unit where the name, the variable, and the unit are all different letters again, and I'm sorry. So, the inductance of a particular object, I'm probably going to alternate saying the inductance of a solenoid versus the inductance of an inductor, but if you have a solenoid plugged into your circuit, the inductance of that object will be equal to the number of loops of that solenoid times the change in flux passing through that solenoid divided by the change in current as the solenoid warms up. So the reason this happens is because once you begin sending current through a circuit, you have changed the amount of flux in the circuit. Once current starts flowing through the wire, there's now going to be a magnetic field that's going to start changing the flux in the system. And the system is resisting that change in flux. So the reason the circuit needs a second to boot up is the circuit is resisting the flux change. Everything resists changes in flux. It fights the flux changes. That's why the ring launcher threw the ring out of itself. So it takes a little bit of time as the flux changes for the current to get up to its maximum level. Now, you don't always know the change in flux, so instead we have a different formula. If you are trying to find the inductance of a specific object, say a specific solenoid that you're plugging into your circuit, that inductance will be equal to the permeability of free space constant, which is a known constant that you will always have access to. I'll go ahead and put it back up on the board now. That constant is 4 pi times 10 to the negative 7th times number of loops in the solenoid squared times the cross-sectional area of the solenoid divided by the physical length of the solenoid. And if you actually go to slide number 12, there is a drawing of said solenoid just showing every axis, number of coils, showing what it physically is as a reminder. And very quickly, just to utilize this formula at least once, the solenoid pictured, we say that I have given some sample numbers. Let's say that it has 50 coils, is 3 centimeters long, and has a cross-sectional area of 0.001 square meter. So, the inductance of that solenoid would be equal to permeability times n squared times A divided by L. So let's start replacing those with the numbers that we know. Permeability is always going to be this number, 4 pi times 10 to the negative 7th. N squared, we have 50 coils, so that's 50 squared, times A, which is 0.0001, and then divided by L. It says that we are 3 centimeters long. This solenoid is 3 centimeters long. That has to be converted to meters first. Remember that. And this will help us solve for the inductance of the particular solenoid listed on this slide. So, let's multiply everything together. And the inductance of this solenoid should be 1.05 times 10 to the negative 5th Henry. So the units of inductance are Henry, presumed for the person who named it. And this is just how you can find the inductance of a specific solenoid. All right, so moving on to slide number 13. When an inductor is in a circuit, and this is what a circuit with an inductor in it looks like. The symbol for an inductor is sort of like a little coil, because, again, a common type of inductor is a solenoid, which is just a wire coil. So this is the symbol for inductor, like how this is the symbol for a resistor. So that's what it looks like in the diagram. This circuit, because it has both a resistor and an inductor, is an RL circuit. Previously, if a circuit had both a resistor and a capacitor in it, it was an RC circuit. This has resistor and an inductor, so this is an RL circuit. And that's just what the drawing looks like. Now, because inductors are sort of the reverse of capacitors, a lot of the same logic applies. That means that this RL circuit will also have a time constant. It will also have a tau. Before, tau was equal to R times C. Here, tau is equal to L divided by R. So you just take the resistance of, you take the inductance of the circuit, you divide it by the resistance of the circuit, and that tells you the time constant of the circuit. Now, the function of the inductor is to cause the current of the circuit to sort of boot up over time. So, what the time constant represents here is, previously, for a capacitor, we were graphing the charge on the capacitor as it charged up. It would charge up to a specific Q max, and the time constant represented when it was at 63.2% charged. But for an inductor, because inductors are not developing charge, instead inductors are allowing certain amounts of current through. If this was an inductance in this RL circuit, tau instead represents how long it takes for 63.2% of the current to build up and start passing through the inductor. So say that we built this circuit, and according to V equals IR, if we had a 1 volt battery and a 1 ohm resistor, the maximum current in the circuit should be 1 amp. Now with an inductor in the circuit, as soon as we close the switch, it's not going to just instantly build up to 1 amp. It's going to start at 0 amps and build up over time. And if the maximum is 1 amp, the time constant, tau, represents how long it would take to build up to 63.2% of that 1 amp. So it takes a certain amount of time for the inductor to let 63.2% of the current through, and that time is tau, the time constant. Previous and additionally, the same rule for 4 times tau being the time needed for a capacitor to fully charge. Here, 4 times tau will represent the time it takes for the capacitor. I misspoke. Here, 4 times tau represents the time it takes for the inductor to let approximately 100% of the maximum current through. So tau still functions the same way, except now, instead of building up charge, we are building up the amount of current that we pass through the circuit. We're building up from 0 amps up to the maximum amount of amps based on what Ohm's law tells us about the circuit. You still find your maximum current the same way. You still do V equals IR, solve for I to find the maximum current. And once the inductor is fully warmed up, that maximum current will be able to flow through the steady state circuit unimpeded. The steady state is the point where everything is warmed up and nothing is changing after that point. So once the inductor has built up all of its charge, the current can flow unimpeded, and it's just going to stay at that maximum current. So steady state refers to we've gone through our charging period, everything's going to stay the same from here on out. You can still find Imax with V equals IR, again, just Ohm's law. And like before, where we were building up charge with a specific formula, that same formula can be modified to show us what the current amount of current moving through the circuit is. And that is this formula here, which is shown to you on slide 14. So if you head to slide 14 next, this formula, I equals V over R, and V over R just is the maximum current the circuit can have running through it, times 1 minus natural log E raised to the T over tau power. This will tell you at T seconds, at a specific moment in time, what the current moving through the circuit is. And that's what this graph still is. So, at a certain interval of time, there's a certain current moving through the circuit. This formula just tells you what it is. This graph is a graph of that formula. And you still work this formula basically the same way as the capacitance one. It's just we have swapped out inductance for capacitance and charge for current. The last formula presented to you as it relates to inductance is this formula here. The inductor needs to warm up. It needs to have a certain amount of energy in it to allow a certain amount of current through it. It's literally warming up. It needs energy to warm up. Once it's warmed up, all the current possible can flow through it. And the formula for the energy that the inductor has is equal to 1/2 times its inductance times the current, which is presently passing through it, squared. I realize this is a lot of formulas, but a lot of this is also a callback to capacitance at RC circuits. We're going to use these formulas in a quick sample, multi-part sample question. So we're going to take the circuit that I've already drawn, we're going to put numbers to it, and we're going to work it out. So, this is going to be a 12-volt circuit. We have a 100 ohm resistor, and our inductor has an inductance of 60 Henry. And we just have a few questions to answer about this circuit based on those values. So, first question. What is the time constant of this circuit? Time constant is tau. We have our formula for the time constant of an RL circuit. We just divide the inductance by the resistance. So, tau will be equal to 60 divided by 100. And that will just be 0.6 seconds. Tau is a time constant, so we do still measure it in seconds, like we did before. So that's part one. Part two. How long will it take this circuit to fully charge? Now, the time constant still represents the amount of time it takes for the circuit to charge up to allow 63.2% of the total current through. The rule for the time it takes to get up to the full amount passing through is still 4 times the time constant. So, 4 times our time constant, 0.06, is going to be 2.4 seconds. So, as soon as we close this switch, it will take this long for 63.2% of the maximum current to start passing through the circuit. After 2.4 seconds, approximately 100% of the maximum current is going to start flowing through this circuit. Just to do the maximum current calculation, so maximum current is going to be circuit voltage divided by R. That's just Ohm's law. So our maximum current will be 12 divided by 100. So our maximum current will be 0.12 amps. So it will take this circuit about 2.4 seconds to warm up. As soon as we turn it on, there's 0 amps flowing through it. After 0.6 seconds, 63.2% of this current will flow through it. After 2.4 seconds, approximately 100% of this 0.12 amps is going to be flowing through the circuit. We've then become charged, and it's going to remain that way until we turn it off. Next question. What will the current in the circuit be 1 second after turning the circuit on? So we want to know the current at a specific moment in time. That moment in time is 1 second after we turn the circuit on. So we're going to come over here to our current as a function of time formula. So current is going to be equal to the maximum current, which is what we just solved for. That would just be 12 over 100 V over R. So the maximum current that we could possibly have is 0.12 amps. That's what this is. Times 1 minus natural logarithm E raised to the negative time over tau. So our time, the time we're looking at is 1 second, and the tau for this circuit is 0.6 seconds. And that's everything plugged into it, so we can find our current with that. Just to refresh everyone's memory about what that E represents and how to use it. That is the natural logarithm E. You access that on your calculator. That's the E here above the ln button. So if you press second and then the ln button, that will put E raised to the something power on your screen. You can then raise it to the -1 divided by 0.6 power. So E raised to the -1 divided by, -1 divided by 0.6. Press enter. That gives us 0.19 approximately. Now that's just this term. That's just this term. We need to do 1 minus what we just found times 0.12. So I'm going to do 0.12 times 1 minus answer. So press enter. And our current at that moment in time should be about 0.097 amps. So we built up to about a little over 3/4 of our total charge at that point. And the last question on this slide. How much energy will the inductor contain in its steady state? Now, steady state means that it's fully charged up, it's fully warmed up, we now have maximum current flowing through it, we're in the state where it's going to stay indefinitely. So, that means when we look at the energy it has in its steady state, we plug in its steady state maximum current, the maximum amount of current that's going to be flowing through it in its steady state. So, we use our energy formula. The energy contained within the inductor is going to be 1/2 times its inductance, that's 60 Henry, times the current flowing through it squared. You do have to square it. So 0.5 times 60 times 0.12 squared gives us 0.432. This is energy, so its units need to be in joules. So that is the amount of energy that this inductor will need to warm up, to get in its steady state, to allow all 0.12 amps of current in this circuit to pass through it. Give everyone a second to look over that. Alrighty. You guys are doing great so far. I believe in you. Alright. Last concept from this slideshow, last new electricity concept. This is about transformers, the electrical component known as a transformer. Now, every single appliance that you have requires a certain amount of power to work right. It needs a certain amount of current, a certain amount of voltage through its resistor to create a certain amount of power. Now, our standard US outlets output a voltage of about 120 volts. Excuse me. US outlets output 120 volts. But not every machine needs 120 volts. 120 volts is just the standard because that's easy to broadcast and it's sort of something universal that we can work with. But not every machine needs the full 120. And so machines tend to come equipped with some blocky brick-shaped thing as part of its plug. Sometimes it's part of the plug. Sometimes it's, depending on your laptop charger, it might be like a weird rectangle in the middle of the cable. Some people tend to call that a brick. I tend to call it a brick because it's just a big blocky thing in the middle of the cord weighing things down. My laptop has its brick as a part of its plug. Sometimes you just got a big blocky plug and the transformer is a part of this. Sometimes the transformer is in the big rectangle in the middle of your cable. The purpose of this brick right here, rather than just the plug ending in the actual prongs, the purpose of this block right here is that it contains the transformer. And the purpose of a transformer is to adjust the incoming voltage to a specific level. So since not every device needs 120 volts, they come with transformers inside of them to adjust the voltage to what they need, to, say, transform the voltage to what they need. So the entire point here of this thing is to adjust the 120 to whatever the device actually needs. Most machines have something like this. Sometimes it's found in the machine itself, sometimes it's part of the plug. Your house, your apartment, whatever you live in, also probably has a transformer, except that looks more like, if you're on slide 16, the transformers on houses and power lines look more like the image on the bottom right of the slide. It's just a device on the side of the box that converts the voltage to what your home needs, and also there are transformers throughout your house that transfer the AC coming in from the power plant into DC for all of your appliances to use. So transformers are incredibly useful. They're the reason most of our machines can work. And if you've ever gone to another country that had a different plug where you would need an adapter, you're not just adapting the literal prongs, you're also adapting the voltage, because this transformer is designed to take the 120 from an American outlet and scale it down to whatever my laptop needs. But if I go to England and say they have a standard voltage of 200, if I use the same transformer there, I'm going to fry my computer, because this transformer is only designed to take in 120 volts. So I need that extra adapter, an extra transformer, to transform Britain's 200 into 120, and then this transformer can take the 120 and turn it into whatever my laptop needs. So, how does a transformer do this? The physical makeup of a transformer, you have some sort of a conductive core. The slide says soft iron. It's some conductive magnetic material, and they wrap coils on one side of it, and they wrap different coils connected to a different wire on the other side of it. So, with my laptop cable, the electricity coming in through these prongs, there's going to be a wire attached to these prongs, and that wire is going to be looped around a piece of iron shaped like that. That wire is going to loop around it and then come back out. On the other side of that piece of iron is a different wire wrapped around that comes out of this end. So there's no actual wire connecting this to this. Instead, the voltage through this wire is going to create a magnetic field. That magnetic field is going to induce, thanks to some assistance from this iron core, it's going to induce a voltage in this cable. And that's going to be the voltage that comes out to your device. So this side is the voltage coming in from the wall. This side is a different voltage going out to the rest of the system. Now, because in physics, there are things like friction and heat that take energy away from the system and that we actually want to use. Transformers do not always work on a 1-to-1 ratio. For most of our math, we are going to assume, unless otherwise indicated, that we are working with ideal transformers, where there is no energy loss, no voltage loss, no current loss, no power loss. Some questions will say, assume you're not working with an ideal transformer, this is your power loss. Unless the question says that, you can assume ideal transformer. And for an ideal transformer, the way that you figure out how much voltage is going to come out of the other side is with this formula. So onto the incoming side, the input side, you send in a certain amount of voltage, and the wire on that side has a certain number of coils wrapped around the transformer, wrapped around the iron. And so this side of the formula is that incoming voltage divided by the number of coils on that side. On the other side, the output voltage is divided by the number of coils on its side. So what causes the actual change from one side to the other is the difference in the coils. If there was only one coil over here, but two coils over here, this side would be getting twice the magnetic field produced by this side, because there's twice as many coils to absorb the field. Well, to be affected by the field, rather. Excuse me. So if this side had twice as many coils as this side, you'd be doubling the voltage. If this side had 5 times more coils than this side, you'd be cutting your voltage down to 1/5. You'd be cutting it down to 1/5. And as long as you're working with an ideal transformer where there's no loss, this formula will help you convert from one side to the other. And so what actually affects the change is just the number of coils on each side. Hypothetically, if you had a transformer with the same number of coils on either side, N1 and N2 would be the same number, and the voltage on both sides would be the same, which would completely defeat the purpose of having a transformer, because it wouldn't be adjusting the voltage at that point. You want a different number of coils on each side, and that's going to affect the actual voltage in and voltage out. Let me just check my notes. All right, so moving on to slide 17. If you're working with an ideal transformer, even though the voltage is going to change from one side to the other, for an ideal transformer, the amount of power going into either side will be the same. For an ideal transformer, where we don't lose any energy to friction and heat and entropy, whatever the power coming into this side is will be the same as the power coming out of this side. So ideally, no power loss. So for an ideal transformer, power on one side equals power on the other side. That means that the current passing through one side times the voltage on the same side should be equal to the current on the other side times the voltage on the other side. Now, again, we can't really make ideal transformers for real, because there's always going to be some loss in everything. If there is some loss, then that just affects the power on the other side. So say that we had 10 watts flowing through this side, and our circuit had an efficiency of 70%. If our transformer was 70% efficient. 70% of 10 watts would be 7 watts. So whatever the efficiency is, that percentage of the incoming amount is what's going to make it through to the other side. If you have an ideal 100% efficient transformer, all of the power will make it through. If your transformer is not ideal, just pay attention to the percentage of how much power makes it through. That will tell you, you can then adjust the power based on that percentage missing. So we're going to use these formulas just for a little bit of practice really quickly. You have managed to construct an ideal transformer. This side of the transformer, the input side, is going to have 265 coils. So N1 is 265. And there will be 50 coils on the output side. So N2 is 50. Question 1. If you run 120 volts, so voltage 1 is 120. If you run 120 volts and 3 amps through the input side, so these are our input voltage and current, what then will be the voltage and current that we get out of the other side? So, first thing I recommend we do is find the voltage. So, V1 over N1 equals V2 over N2 for an ideal transformer. So, our incoming voltage is 120 volts divided by the number of coils on this side, 265. On the opposite side, we're solving for our output voltage, and that side has 50 coils. So, multiply both sides by 50 to get V2 by itself, and that will tell you the output voltage on that side. So, the output voltage will be about 22.6 volts. 22.6 volts. We have stepped our voltage down. We've stepped our voltage down. Excuse me, I'm sorry. Now, to figure out how much current is going to come through to the other side, we can turn to this formula here. If we're assuming ideal transformer, 100% of the power is going to make it through. So, the starting voltage, or starting current times the starting voltage, so 3 amps times 120 volts should equal the current on the other side times the voltage on the other side. So we just found the voltage. That times the second side's current must be equal to the total power from the other side. So, multiply these two together, divide by 22.6, and that will tell us what the current coming out of the output side is. And that should give us about 15.9 amps. Notice, even though the voltage went down, the current went up. That tends to be how the transformers work. If you step voltage down, you step current up. If you step voltage up, you step current down. So in addition to modulating the voltage coming in, you can also use a transformer to modulate the current coming in case the current is specifically what you need to limit on your circuit. Now the last question is looking at, instead of an ideal transformer, what if it was instead a transformer with an efficiency of 75%? So, with 75% efficiency, only 75% of our starting power is going to make it through. So, we need to figure out how much power is on the primary side. Power is equal to, well, there's lots of ways to find it, but the formula that is most convenient for us right now is P equals I times V, because we know both the current and the voltage on the incoming side. So to find our incoming power, just multiply the incoming current by the incoming voltage. That's going to be 3 times 120. So our incoming power should be 360 watts. That's our incoming power. If we are 75% efficient, then only 75% of this power is going to make it through. Which means instead of getting 360 watts, the output side would get 270 watts. This number is 75% of this number. And step back, let everyone copy. And with that, that is every formula gone over briefly from our electricity chapters. So this is the last Monday posted video lecture for electricity. This week we are going to review these principles. Towards the end of the week we will start on test review. Our test will be at, I will post the test so that you can take it next week. I'm still working out the details, but I'm going to try to make it so that you can start it whenever you are available for it. There will just be a timer so that once you start it, you have to finish it within a certain amount of time. I will make that available for you to take it next week. We will spend the end of this week and the beginning of next week studying for that test. I will post practice questions and everything. So you'll have ample time to prepare, ample time to ask me as many questions as you have. But at least for this week, for right now, continue going over this material. Come prepared to the study sessions with questions. We will go over this. It is our last electricity chapter, so let's finish strong. And thank you all. Hope you have a great day. Bye.